Today we're going to be solving a problem that's written on the bottom of the slide. So we have a freight train that enters a tunnel with a speed of u naught. The front of the train spent twice as much time in the tunnel as the end of the train. What was the speed of the train when the last car left the tunnel? The length of the train was equal to the length of the tunnel. And we're going to assume that the train moved with a constant acceleration. So let's see what's going on. There are actually three figures we want to make. Here they are. The first figure tells us that, this is the situation when the train just about to enter the tunnel. It has a velocity of u naught. Okay? So sometime later, the train is fully in the tunnel and about to come out. The front of the train is about to come out from the tunnel. And that's the train at that time moves with velocity u1. Since the length of the train is the same as the length of the tunnel, when the front of the train is getting out of the tunnel, the back of the train is just getting into the tunnel. And the last situation is the very end, where figure 3, where the back of the train just came out from the tunnel. In this case, velocity of the train is u2. So how are we going to solve this problem? First, we were told that the train moves with constant acceleration. It moves along a straight line. So we can use the formulas for constant acceleration case. So here are two main formulas that we need to know. The first formula is for coordinate along which the train is going with constant acceleration. So the coordinate x is going to be moving from the left to the right. We will assume that 0x corresponds to the left side of the tunnel. And in this case, the right side of the tunnel will have coordinate, let's say, L. Okay? Nobody told us what the length of the tunnel is. We just assume now the length of the tunnel is L. Well, that's what you normally do when you need some variable. You think you need a variable, or you need some value which you don't have. Okay? In this case, you just make it up. And hopefully at the end, this value, you will either find this value or it's just gonna cancel out, disappear. Okay? So the first equation is for coordinate. The second equation for the velocity. So from the first equation for coordinate x, you'll see if t time equals to 0, x is going to be equal to x naught. So that is initial position, or a position of an object at time t equals to 0. Okay? If we put t equals to 0 in the second equation, we find that v equals v naught. So it tells you that v naught is the velocity of an object at t equals to 0. And a is acceleration. Okay? Again, we don't know what it is. We know it's constant, so it is a constant. And hopefully we won't need it later. Okay? So those are two main formulas that you need to know when you deal with constant movement with constant acceleration. So there are a couple more formulas that it's useful to know. And these are those formulas. These formulas actually obtained from the first two. And they could be used, for example, formula number 3 could be used when we don't know time, t, or we don't care about the time. Nobody gave it to us. We're not interested in that. The formula 3 may be useful in this case. The fourth formula does not have acceleration. So it could be useful when we don't have acceleration. Okay? So for this particular problem, we are interested in formula 2, and formula 4. Let me get these two formulas, and let me rewrite them at the very top so we won't forget about them. So what do we do now? We consider, let's look, apply these formulas for the picture in figure 2. Okay? So this is what we're going to see. So we're going to assume that t equals to 0 is the situation in figure 1. Okay? And the other situation we're interested in is figure 2. Okay? So in the first formula, what we see, u1, velocity of the train, or velocity of the, in this case we're considering the front end of the train, is going to be equal to the velocity of the front end at the time when figure 1 was taken, and that velocity will be u0, plus a times time between these actually two moments. Okay? And that time I'm going to denote as t12. Okay? It's the time it takes for the train to move within the tunnel. Okay? So it's the time that the front end of the train travels within the tunnel. Okay? So if you look at the second formula, what we see on the left is the distance the front end travel in this time, and the distance is the length of the train or the length of the tunnel, and that is L. Okay? Again, velocity, we already said that the initial velocity is u0, the other velocity is u1, and the time it took front end to go through the tunnel is t12. Okay? Now let's consider what's going on between figure 2 and figure 3. Now, here's one thing. We're going to consider this as kind of a separate problem. We'll consider t equals to 0 as what we see in figure 2. And we're going to say in this case, what's going on in figure 3 is time t23. Okay? And the point we're going to be interested in is the rear end of the train. Okay. So here's the formulas, how they're going to look. In this case, for the rear end, we consider t equals to 0 the figure 2. So our v0 will be u1. Our v will be u2 when the rear end of the train gets out from the tunnel. Now, when we look at the other formula, we see that x minus x0 is the distance that the rear end travel, and that's going to be L again. Again, v and v0 we said as u2 and u1, and the time the rear end travel within the tunnel is t23. Okay? Now, we were told that the front end spent twice as much time as the rear end, which means that t12 should be 2 times t23, right? So, and now we kind of ready to solve this problem, solve this equation. So first, let's concentrate on the left equations, okay? So first what we're going to do, we're going to replace t12 with 2 times t23 in the first equation. In this case, these two equations are going to be written the way they're written here. Now what we're going to do, we're going to multiply the second equation by 2, and then we take that equation and subtract the first equation from that equation, okay? So on the left, as you see, we're going to get 2u1 minus 2u2 minus u1. Now, on the right, we're going to have 2u1 minus u naught, and the last term is going to cancel. Okay? Now, what we're going to do, we're going to clean these things a little bit up. We're going to move u1 to the other side of the equation, and we're going to have an equation like this. Okay? Now, let's put it at the very top, so we still remember it. And now we're going to deal with the second set of equations. And what we're going to do now, first of all, yes, we're going to replace T12 with 2 times T23. Okay, the first equation. This is what we're going to do. That's what we're going to get. And the next thing we're going to do, we're going to divide the top equation. You can take this first equation, this one, and divide it by this equation, the second one. This is what we're going to do. L over L gives us 1. And in the right-hand side, you'll see that T23 cancels out. So the only variables we have now is u0, u1, u2. Okay? Now we're going to multiply both sides of this equation by our denominator, u2 plus u1. This is what we're going to get. And again, we're going to clean this thing a little bit up. So we're going to take this u1 and move to the other side. And this is what we're going to have. All right? Now we're going to just keep those two equations with us. And the next thing we're going to do, we're going to take the second equation and multiply it by 3. And then we're going to take this second equation, take it and subtract the first equation from it. Okay? In this case, we get 3u2 minus 2u2. I get just 1u2. 3u1 and 3u1 here are going to cancel out. And here I have 6u1 minus 1u1 minus u0. We're going to get that u2 equals 7u0. So this is it. The problem is solved.